Hello and welcome to today's webinar from Hydromantis. We're going to be talking today about setting up BNR layouts, biological nutrient removal layouts in GPSX. I'm going to be spending a little time running through what are the typical things that you need to think about and what are the typical things that you need to set up and where you can find those elements and all the various menus and bits and pieces of GPSX, and I'll be giving you a few tips and different things to kind of help along that process. So my name is Spencer Snolling. As you may know, I've been part of Hydromantis for over 15 years and spent most of that time helping to develop GPSX. I'm glad to be here with you today in what is turning out to be the deep freeze here in Hamilton, Ontario, Canada. It's about minus 14 degrees Celsius at the moment. And we're expecting it to be about minus 22 or 23 Celsius overnight here. So I hope you're staying warm wherever you are. So my plan for today is to talk about typical things that you need to think about when you are setting up a BNR plant in GPSX. This isn't really going to be a webinar about BNR design. This is more here to help you sort of understand where are all the settings that you need, and a bit more of a instructional lesson on using the software and finding the appropriate settings in the manuals. So I'm going to go through a number of slides to sort of illustrate where all the important things are. Then I'm going to do a quick desktop demonstration by building a plant and showing you all of the steps along the way. I also thought it would be worthwhile to take a moment to illustrate all the ways that you can get the output from your model out of GPSX. As you know, if you are a regular user, there's a very large number of different types of output graphs and tables and windows and panels and all sorts of stuff that you can use in order to make GPSX display the information that's coming out of that model. The reason it's like that is that we've spent quite a bit of time, particularly in the last 3 or 4 releases of the software, to try and make it so you can get the information that you want easily. So we have a lot of options to access the numbers and plot them in different ways, and hopefully we've got those all in a way that's useful for you. I also have a couple of slides at the end that are sort of just a hodgepodge of somewhat random items that I know are important when you're trying to do BNR design or optimization of an existing plant, and so I thought I'd throw a few of those in there at the end. And lastly, I'll talk a little bit about the large number of plant models that we already have designed and put together that come as part of GPSX when you install it, and show you where to access that. And a few final thoughts at the end. And as always, you can ask questions along the way. Hopefully I'll be the one answering them. Ask questions along the way by typing them into the questions box that's part of your GoToWebinar dashboard. Usually the way we do this is that you type the questions in at any point along the way, and then I'll store them up, and then we'll, at the end of the webinar, we'll spend a bit of time. I usually hang around for 5 or 10 minutes and answer questions at the end. Okay, moving on to our topic for the day, looking at biological nutrient removal. So just to define what we're doing here in the context of this particular webinar is biological nutrient removal, nitrogen and phosphorus removal, in addition to the regular COD removal you get in a plant. And I'm going to be talking for the most part today about conventional activated sludge, so suspended growth systems, no biofilm systems today. Usually these are, of course, some sort of combination of plug flow tanks or CSTRs in series, and they are set up to have a number of zones that are anaerobic, anoxic, or aerobic, and then some recycles and other things to sort of, force that biological process into the position where you want it so that you can get it to do what you need it to do. So in general, something that looks like this. This is drawn on a GPSX drawing board here, Influent, some sort of primary clarifier, some number of bioreactors that may or may not have some recycles included, and a secondary clarifier. Okay, so there are basically 4 things that you need to consider when you're setting up a BNR system in GPSX. First of all is the reactor volumes themselves and the way that they're laid out and hooked together. The aeration settings, obviously if we're going to try and control where we have an anoxic zone versus where we have an aerobic zone, we want to be able to get our airflow distributed properly. Recycle flows, and by that I'm mostly speaking of the internal mixed liquor recycle, so flows that take things from you know, an aerated zone back to an anoxic zone or an anaerobic area. Those types of things, I'll show you where you set those up. And then lastly, the Influent and RAS distribution. And by that I mean flows that are coming into that unit process can be distributed down the length of that plug flow reactor if you like. By default, they are not. So for example, if you were trying to do step feeding, we can show where how you set that up. Now, just a few words about using the plug flow objects versus the CSTR objects. So this little image that I showed you on the previous slide there shows a BNR type system that is done with completely mixed reactors. Now, these are the anoxic ones. There's no bubbles in those. And here's an aerated zone, and there's some recycles and RAS flow and so on, all drawn out there explicitly on the board. Now, you can certainly go ahead and do it that way, and then lots of people do, and I've had projects where I've wanted to do it that way as well. However, this is basically exactly the same as doing it with one single plug flow object in GPSX. And this version actually has a number of advantages to do it this way. But just to let you know that really this object, which shows sort of a number of zones in series and with some aeration settings, and you can see the influent distribution across the top there, that's set up because there are some nice advantages that we can take advantage of and features that are there when you do it this way. But basically, you're going to get mathematically exactly the same answer, whether you do it this way, drawn out on the board, or whether you use the plug flow icon that is shown there. Now, for the remainder of the webinar, for the most part, I'm just going to be talking about this methodology down here. The plug flow object, as I said, has several advantages. I find it easier to configure because all of the settings are in one menu. So basically, if you're trying to organize yourself and get your aeration settings and your recycle set up properly, it's all together in one place because it's all in one object. It certainly saves space on your drawing board, especially if you have parallel lines or something that's complicated where you have some combined RAS coming back or something. You know, you have a lot of lines on your drawing board. It's nice to be able to save some space there. There's better default settings for aeration, some of the aeration settings, if you use the plug flow tank. For example, if I were to do what I was showing earlier and drop 3 CSTRs in a row and hook them up, they are going to have the same default settings for things like alpha, for example. However, if I use one plug flow tank, then our defaults are already tapered along the length of the tank. So that allows you to have, you know, possibly somewhat more accurate settings right off the bat before you start doing your calibration. And of course, the output, this is probably the most useful part, is the fact that the output is now all organized into arrays for you to be able to plot them on bar charts and other types of graphs and put them in tables and things. This means that all of the results that come out of that particular unit are nice and easy to convert into forms of output that you can see and use quite easily. As I said, both methodologies are there and both are totally valid. I just find the plug flow reactor, and I think most people do who use GPSX, the plug flow is sort of the easier way to go. Right, so just to show you about the difference in that output that comes along, if you throw, as I said, 3 CSTRs down like this, really what you're doing if you want to plot the ammonia, say in all 3 of those one after the other, you're going to be really have no choice but to do it, if you want to put them all on one graph, on an XY graph like this, and you know, use this axis to note that this is the first tank and this is the second tank and the third tank. So you kind of have to know you know, which one is which and go by the colors that you have. Whereas that exact same thing done with a plug flow tank allows you to plot this kind of a bar graph. So you can, you know, clearly see, you know, in sequential order as you go downstream what the concentrations are. Okay, so that's the reason why we like to use the plug flow tank object instead of a bunch of CSTRs hooked together on the drawing board. Okay, so now moving on. The first of those 4 elements, as I mentioned, was setting the reactor volumes, and that is done in the physical menu. So that's done by right-clicking on the object, going to input parameters, and then bringing up this physical menu. So the first key thing there is number of reactors in series, and that's something you can measure in reality by doing a dye test or so on. But for the most part, you're going to choose, the conventional way to do it is to choose the number of reactors to be equal to the number of passes or zones in your BNR design. You could even choose it to be larger than that, so you have a couple of reactors in each of those zones if you feel that that's the way it is hydraulically. But for the most part, most people tend to say, well, if I've got 3 passes or 4 passes in my Barden flow system, for example, then I'm going to set this to 4 reactors in series. Then once that's done, you can set up the volume for each of those reactors. There's 2 different ways you can do it. This volume fractions that we're showing here on this slide right now says that you set the overall maximum volume, which is down here, and then you set the fraction for how you want to divide up that volume. So you set percentages for each of them. And by default, we set it up so that they're evenly divided. You'll end up with 4 reactors in series, each of the same volume. And then you can go in and tailor that the way that you need to do it. The other way to do it is to pull down this menu and select the individual volumes, and then you hit this button and you do it that way. So the reason we allow for this methodology is it's actually quite useful if you are doing a design of a plant that's not been built yet. And I know how I want my zones to be sized relative to each other, but now I'd like to sort of scale the whole thing up or down, and that's why it's a sort of a useful setting that way. Again, both methodologies are available there for you to use. Okay, moving on to number 2, aeration settings. Now, when you're setting up your design here for your biological removal, you're likely going to need an anoxic zone at the very least, or possibly an aerobic zone too. So you are going to do that by deciding where the air is going to be, and that's through either choosing a bunch of DO set points and letting the DO controller tune up the air appropriately. Or you can set that airflow directly, or if you're doing a mechanically surface aerated plant, use the mechanical aeration option and set the power directly. Now that is done by using the operational menu here. So right-click on the object, go to Input Parameters, and then click on Operational, and it brings up this menu. This is where most of the interesting stuff is found in these objects. Now, what you'll find is that first of all, you pick which kind of aeration system that you're using, and then you can decide whether you want to enter it in by DO set point or enter it in by airflow directly. And you can, for example, here, by setting the airflow directly, you can specify the distribution of the air into those zones, whatever number of zones you've put in series. So here, for example, when I click on that button, we can see that this is 3 tanks in series, and there's a small anoxic zone up front where there's less of it there. Oh, I'm sorry, that should... yeah, that's right. That's correct. It adds up to 100%. That's what you want it to see. So you've got 0 at the front and then 50-50 divided in the back 2 zones. Okay, so that's aeration settings. Now moving on to the third of the 4 items that I mentioned. The third one is defining the internal mixed liquor recycle flow. So this is for when you want to move some flow, usually from downstream in some of your areas upstream to back into one of the earlier zones. Now, the way that that is done is accessed, again, through that same operational parameter menu that I mentioned before. Now, the aeration settings are at the top. This is found down at the very bottom. Internal recycle is what it's referred to as here. And when you click on that button, you get a special menu that looks different than all the other ones in GPSX. And what it does is you specify by which zone or which number of reactor in series that you want to do. So let's pretend that we have something that looks like the example that I gave you before, where we have 3 tanks in series. And I'm going to do this with a plug flow tank instead. And I want to be able to put in this internal recycle. If I was doing it explicitly with the CSTRs like it's done here, you draw that internal recycle right on the board. However, in the plug flow tank, you don't even need to do that. It's much simpler to go to that internal recycles menu and pop it up. And it looks like this. And you specify, I want to have a recycle flow from this reactor to this reactor, and then you specify the flow rate at which that happens. So it's pretty straightforward. You can make as many of these as you like, all the way down. I believe actually the maximum is 10. I don't think I've ever seen a system that had anywhere close to that. But you can specify several of these, specify what their default flow rates are, and then that gets included into the model, and you can put it on a slider or change it in a scenario just like you can any other parameter in GPSX. But this has to be done during the modeling part of the exercise. So this is done when you're in modeling mode, when you're in the drawing board area, and then that gets built in and compiled appropriately. Okay, Now on to number 4. The last one of the 4 items that you have to consider is the distribution of the incoming flows that are coming into the head of that particular object. So in this case, that is influent, the stuff that's coming from upstream. You know, this is potentially coming from, say, the primary clarifiers. And the RAS, the recycle, coming back from the secondary clarifiers is going to come into this particular head of this reactor in series. So by default, these are set to go 100% into the front tank. So it goes into the head of the system by default. However, you could potentially change that and have it so that it is distributed in a different way. So for example, you could divide that evenly up and have it set so that it goes into evenly all 4 reactors going downstream, and you can do it in whatever way that you like. This is how you would do step feeding if you were using it, say, for wet weather control, or there, of course, are certain types of BIOP systems that require you to put a little bit of your influent a little bit farther down the stream for carbon purposes or what have you. So this is where this is the kind of thing you would want to do. You can also do it with the RAS as well. By default, it all goes in the front, but you could choose to change that and have it go into some of the later downstream tanks as well. Okay, where do we find that? Again, back to that operational menu again. And I was showing you internal recycle before. Now is the ones just directly above that, influent fractions and recycle fractions. So as I mentioned, by default, it's all going to be 100% coming in the front end, just as we've shown here. And this is for influent fraction example. And you can change this to be whatever you want. Just make sure it adds up to 100%. You'll get a little prompt up in the window that tells you if it doesn't add up to 100%. But you can change that to whatever you like. Okay, so that's a lot of information. I think probably the easiest way for me to sort of really pass on the important part is for a demonstration. So we'll hop over here to GPSX. What I'm going to do is I'm going to build a typical MLE system. I just scanned this little image right out of Metcalfe and Eddy. So we're going to be doing an MLE system, 2 zones. It's doing nitrification and denitrification. It's got an internal recycle. So it's got everything that we need to look at from those slides that I just mentioned. Okay, so here's GPSX. I'm using version 6.4, by the way. Hopefully all those of you out there are up to the most latest version, 6.4. And what I'm going to do is I'm going to start by grabbing the wastewater influent icon. And we're going to configure this, just for this example today, to make it look like it's a primary effluent. And as you may know, when you go into the composition menu in GPSX, our little influent characterization tool, I shouldn't say it takes up the whole screen. What this does is this allows you to specify what the influent concentrations are, and it does a little bit of data reconciliation for you as well, by just making sure that all the calculations that get it into those state variables are appropriate. Now, the nice thing to know is these are all default values that we have here. What I'm going to do is I'm going to switch, these are the ones for raw. I'm going to switch over to our set of default parameters by clicking on this primary button here, and you can see that it's made some changes to the concentrations, and most importantly to the fractions here as part of that influent characterization. Okay, so we now have ratios and stoichiometry that is appropriate for a primary effluent coming out here. And I'm also, just on top of that, going to change this up to 50. Just to make this a little bit more challenging example to show you. So let's accept that. Now what I'm going to do is grab a plug flow tank here. We'll put that on, and I'm going to hook that up, that flow right there. And I'm going to grab a circular secondary clarifier, and we're going to put this on here like this. And let's connect our RAS line around to the front again. And that's all we need to do for our little BNR system. We're only modeling the activated sludge part of it today. Okay, so what I want to do is now configure those 4 items that I mentioned before. The reactor volumes, the aeration settings, the internal mixed liquor recycle, and then the influent and RAS settings as well. So I go to, first of all, the physical menu. This is where you set the number of reactors in series, and then you can set their volume. So what I'm going to do is I'm going to switch this from 4 to 2 because we're going to do simple MLE, which is just going to be the 2 reactors in series. And I can come down here to volume fractions, and I can see this is split 50-50 right now, 50%. So 50% of it will be the anoxic zone and 50% of it will be the aerobic zone. And we'll just leave it like that for now. So I'm going to hit accept. Now, moving on to the aeration settings, let's go to the second menu here, operational. This is where we find all the things to do with how you operate your tank, such as aeration settings, distributions and pumping and all of that stuff. And by default, we use diffused air. I'm just going to leave it like that for this example today. And I could either enter the airflow directly, or I could use a DO controller. And I think today I'm just going to use the DO controller setting that's showing there. And then that means I click on this button to set the DO set points for all of the zones that we're doing. There's only 2 of them for the example that we have now. And I'm going to make the first one 0 so that it's now set an anoxic zone at the front half of this system. So we have an anoxic zone followed by an aerobic zone. Okay. That was the second step. Third step is to go down to the bottom of this menu and click on the internal recycle. So now, as we mentioned before, and in fact, I'm just going to pop this slide back up again just so that we can see that we have to take an internal recycle here from the aerobic zone back to the anoxic zone. So it's taking all that nitrate back there to be denitrified at the anoxic zone at the front part with all that carbon coming in. So that means I need to go from zone 2 to zone 1, and I'm going to enter in the flow rate of 2,000 meters cubed per day, which is by default. Actually, this is the same as the influent flow. So this is 1 Q internal recycle. Okay, so that's that. That's our internal recycle, and then now we would, of course, set any other changes that we want to do to the influent fractions, which now comes all directly into the front of the reactor, and of course that's the way we want it to be, so no changes there. And also the RAS coming back from the secondary clarifier, again we want that all to go into the front of that reactor, so no changes required there. Okay, so we have all 4 sets done of all of the information that we need. So we're now ready to build our model and run it. So let's pop over to simulation mode, and the Fortran compiler is going to do its little job there and build us a model. All right, so there's lots of things that we can look at here in terms of running simulations and getting information out. But just to keep things simple to start, I am going to grab a couple of the parameters that we had there that we had set so that we can play around with those a little bit. And one of them is I'm going to put the volume fractions up here. I just dragged them up onto our input panel. And what that's done is that's allowed us to have these available handy little sliders here to make changes, and allow us to be able to adjust the relative size of the anoxic zone versus the aerobic zone. And the other thing I want to do is that mixed liquor internal recycle. So that's down at the bottom here, click here, and I'm going to drag that up here as well. And now we can adjust that flow rate. Okay, so let's take a look at what kind of results we get. Well, I'm just going to run it once at all of the settings that we currently have here. And so what we're going to see is, right now I'm looking at the clarifier. This column here is actually the effluent from that clarifier. And we can see that, for example, that our ammonia is 0.7, and the TKN, or pardon me, total nitrogen coming out the back end of the tank is 17.1. So we're getting lots of nitrification, and we're getting probably some denitrification there, actually a fair bit. Remember, it was 50 for TKN going in. So we're getting, obviously, both nitrification and denitrification, but now the model allows us to play around with some of this input to try and improve things a little bit. So what if we were to split this to be, say, 0.4 and 0.6? So that, in other words, it was 40% anoxic and 60% aerobic. That gives us a little bit of a more aerobic zone. Maybe we can push this ammonia down a little bit. So let's rerun that, and it went down from 0.7 down to 0.56. So that is an improvement. We got a little bit more nitrification happening, but as you can imagine, that has come at the cost of our anoxic zone, so we're not getting quite as much denitrification as we had before. So now nitrate instead of 12 is 13, and our overall total nitrogen went from 17.1 up to 17.8. So that's not much of an improvement overall, and in fact, in terms of total nitrogen, we went up a little bit. Well, what if we actually were to increase the mixed liquor? So these are the kinds of things you can do with the model. Let's push that up a little bit. So now we're at about 1.5 Q. Well, it came back down to 16. That's a little bit better. What if we go way up here? I'm just going to type it in. Let's do like 8,000. So now that's 4 Q. And okay, it comes down to 16. So you know it doesn't seem to be totally limited by the amount of internal recycle. Maybe we'll be able to knock that back a little bit and save on some energy without actually having to do all that internal recycle. Well, 16.7. No, I think basically we're short on anoxic zone. So let's put these back to what they were before by clicking on these reset buttons. So now we're back to our original anoxic zone, and so let's run that again. Okay, so the combination of the higher internal recycle and having at least enough anoxic zone to get some denitrification got us all the way down to 13. So we dropped it by another 4 milligrams per liter almost compared to what we had by just the default settings that we put in there. So that's a good little example of how you set up a BNR plant in GPSX and a couple of the typical things that you would do to play around and understand your system. You know, that's the great part that modeling can do for you. Okay, so moving on from that, last few thoughts here. There's a few different ways to get output out of GPSX. As I mentioned, there's lots of different ways. Here's some examples. You know, the output variables menus themselves actually display all of the results that are happening. We have the bar graphs and time series graphs, those quick panels, which is what we were just looking at now. There's tables that you can generate. You can generate reports out to Excel spreadsheets. So just to highlight a few of them, this is the quick panel here. These come up automatically for you when you build a new layout, or at any time you can double click on them to create some new ones. So looking at the one for the bioreactor, this little table here basically shows us, for example, the ammonia coming into the front end of the object up here, and then we have you know, goes from 25 to 7 to 0.27. And that gives us a way of looking at some of the concentrations as we go through these various objects. That's with the nitrate going up as it goes through. So this is one way, and you can copy and cut and paste this information into an Excel spreadsheet if you like. As I mentioned, even going to this output variables menu, to go to state variables, any one of these things can be plotted directly. You can take a look at these values just by popping these little menus up. You can see some of the output from the model. But what I think most people like to do, and this is part of our tutorial 1 exercise, is to drag these things onto bar graphs. So we can do that here. That's ammonia, nitrite, nitrate, and let's throw readily biodegradable substrate up there. You can put alkalinity, you can put all the different rates, OUR and all that kind of stuff. Any one of those variables that were on that menu can be plotted. And then when you do this, you get a bar graph that shows that. And this is particularly useful for when you have lots of reactors in series, and you can see the profile as maybe you get, you know, phosphorus uptake, and then you get release, and so on. And those are all the really sort of nice intuitive graphs. I quite like using these a lot, and you can of course change the colors of them and so on this menu here. And I have this little sort of color palette in my head that I use frequently to keep all of my state variables correct. Okay, so that's another good example of ways you can get at that. I'll also briefly mention this. This is a relatively new feature in GPSX, the Table tab. You can click here. You can create a table that plots all of the types of variables that you would like to see for all of the objects that you would like to see in the GPSX layout. I'm just going to leave everything turned on here, but you can create a table such as this. This is now plotting ammonia actually all the way throughout the whole plant. So this is quite interesting the way you can customize this table, take certain columns in and out to be able to see right from the front end of the plant to the back end of the plant, you know, what the total nitrogen was like, and you can even plot a bar graph out of that as well. Now this one's not all that interesting to look at because it's fully nitrifying, but here's the ammonia coming in the front, and the first part of the reactor, second part of the reactor, all the layers of the clarifier, and then on out the back. So, but you can plot a lot of different graphs from there, and all of this can be exported out to an Excel spreadsheet with that button up there. Okay, so lots of ways to get at the results of your model. Okay, and I have a few last second thoughts that I'd like to mention about various other parts. Oh, I should mention the GPSX configured layouts that are part of your installation of GPSX. Everybody who has a GPSX license has all of these layouts made for you. You may know that in this sample layouts menu here, we have about, I think there's over 60 now, different types of plants and layouts and exercises already put together for you. So when you bring that up here, we've organized all of this material in by viewing these 3 windows here, and we have different plants broken down into COD removal, removal and COD and nitrification, COD nitrification and denitrification, and then BioP. And then there's a few other process examples for things like MBRs and IFAS and so on, and all of our tutorials are here as well. So let's look at the BioP layouts here. You can see that we have various different types of plants, and the descriptions of those plants are shown over here along with an image of that. You can see here, again, we're using just those 3 objects to describe the biological process here, but we've already configured the internal mixed liquor. We've sized the tank. The recycles are there. The DO set points and the aeration settings are all done. So you can just pop in here, pick out one of these plants, and then just enter in your own flows and sizes and then go from there. So it's all nicely set up for you easily. Okay. A few extra thoughts just at the end here. We have this kind of information available to you as part of Influent Advisor. As I was mentioning when I first started that example on the desktop there, there's a lot of calculations done on the Influent data right off the bat for you automatically. This can be found in the bottom right-hand corner of the Influent Advisor menu. You may have to scroll down to actually find it, but what it's going to give you is the nitrogen to COD ratio or the phosphorus to COD ratio, and there's a few other things here. That can, of course, be very handy information when you're trying to configure your plant by looking at the appropriate levels of carbon that are available to do denitrification or to do phosphorus removal as well. And that's very handy for you. You can display this here. You can even use this little button to flip the ratio or the other way around if you would prefer. We also have a couple of objects that have 2 inlets on the front, and that is for doing methanol or acetate addition. And they can be done where you can distribute the carbon addition that you're putting in there, actually any point along the length of that plug flow system. Now, this is called the dual inlet plug flow tank, and it's actually found just underneath the regular plug flow tank. And if you wondered what the difference was, or why do we have this one with an extra connector on it, normally you put the Influent wastewater actually into this particular connection point here, and of course the RAS goes in the lower one. And then the carbon dosage actually goes in the top. And then just like the other Influent fractionation that we had before, where you can decide where to distribute down the length of that plug flow tank, here it's called Influent number 2. I realize that's a little bit counterintuitive. Number 2 is on the top. But Influent number 2 is where you set up that carbon dosage, and then you could potentially have something that looks like this. This is the object we have in GPSX. You can find it in the Influent panel. That is used for adding things like methanol or acetate or other synthetic type of carbon addition like micro C and micro G and that kind of stuff. You can all configure that sort of thing here, and then you could say this is coming in and it's going into the 3rd tank, for example. And lastly, there are a few other objects in GPSX that have these same settings. So right now I was just showing you conventional activated sludge, but I would like to mention that the MBR membrane bioreactor, we have a plug flow version of that where the membrane's at the end. This has more or less the same settings that I was just showing you, except for it only has one Influent connection on the front. The hybrid object, which is the floating media in suspended conventional activated sludge, that where we use for IFAS or MBBR, that also uses this same type of process with setting up and recycles, and you can even control whether you want to let the media move with the recycle or not. And then HPO, that's another one, high purity oxygen, where you can do some different settings for all of those down in series. So all of those different things, the tanks in series, aeration settings, internal recycles, and then the Influent RAS specification should allow you to do basically any BNR configuration that you can think of. Sometimes you may have to be creative with the way that you set it up, or you may have to connect to plug flow tanks in series to get exactly what you need. But I haven't yet met one that we couldn't do.